Welcome to this presentation. This will be a short presentation. I have linked to a YouTube video, How to Think About Data Visualization by Jake Vanderplas. This is an excellent presentation. It goes to depth to talk about the principles of visualizations as well as the use of the alter package to do visualization in Python. The purpose of my presentation here is just to overview the theoretical underpinning principles for information visualization. The question is, why visualization? Why do we use visualization? Now, intuitively, the answer is that, well, a picture is worth 1,000 words. We can condense and convey much more information in a picture than in, comparably trying to express this information in written words or numbers. But why is it the case? Let's take a look at this data here. And my question to you is, well, try to identify extreme values in this data. Okay, so you're probably reading through the data and trying to compare and contrast and make some conclusions. Now, how about if I ask you the question and I highlight some of these extreme values? One of the reactions I get when I ask students after conducting this exercise is that, well, you have highlighted these numbers to us. In my response is that, well, I have highlighted them, but why is highlighting them any different than expressing them in written numbers? After all, a written number is a shape, right? Each digit has a shape. A written number also has a color, right? All of them are black. If I highlight them, the numbers are still shapes, right? But there is an extra piece of information, which is color. Now, of course, here there are two important points. One of them is that there is now a contrast between extreme values and non-extreme values as expressed by colors. But again, that construct existed before because these numbers were written in different shapes. The key difference is that when trying to answer this question prior to highlighting, we're trying to cognize about these numbers. We're trying to think and engage our cognition. Maybe thinking about keeping track of, different anchor numbers, the smaller so far, larger so far, what's small, what's two digits, what is in 3 digits, what has a 9, what has, 3 or 2. That's all cognition. When we do use color, we don't use cognition anymore, we use perception. And it's really important to differentiate between the human cognition system and the human perception systems. Let's take a look at this example here. This is basically summary statistics of one data. Summary statistics are usually used to condense a large data set into fewer kind of indicator numbers, such as mean, variance, correlation. In this case, each observation has an X and an Y value, and I am reporting the X mean, then the X variance, the Y mean, and the Y variance, as well as the XY correlation. So one approach to condense large data is to present it in summary statistics. But the summary statistics also kind of forego a lot of the nuances that this data has. Indeed, this is a very kind of famous data set called the Anscombe Quartet. And basic idea behind this data is that, well, those summary statistics are the summary statistics of all of the 4 data sets you have here. And those 4 data sets, as you can see, are completely different. Again, the key point in here is as you can see, because when I visualize the data to you, kind of in contrast to when you look at the numbers, you can quickly detect patterns, you can quickly detect relationships, and you don't even need to think about it. You can see that one of them is almost linear. This one is not linear, it's quadratic. This one is linear, but you have an outlier. This is not linear, and you've got an outlier as well. So the two benefits of visualization is that we can condense a large number of information, of data points, and we can use the human perception system. So Thinking Fast and Slow is a famous book written by Nobel laureate Daniel Kahneman. And in this book, which is a great read if you haven't read it, he talks about System 1 and System 2. We have 2 systems. One of them is fast and intuitive, We don't even think when we engage this system. And the other one is slow and contemplative. So when you get and drive your car, you're engaging, if you're a trained driver, you're engaging the intuitive system. You don't even think about what you're doing. All of this happens without you thinking. If you're trying to solve a math problem, it's a different story. You're trying to engage cognition. And it turns out that many problems in automation, in information systems, that we thought are very difficult to resolve until very recently were problems of perception. Things like face recognition, pattern identification, speech recognition, that were now, until recently, until the recent development in machine learning and AI, were completely out of reach. People do these problems, solve these problems very fast. The irony is that problems we thought are difficult were easy, and problems we thought easy were difficult. So a problem like multiplying two numbers, it's very difficult to the average person, and even for a trained person, it will take kind of a large amount of time if the numbers are sufficiently big. This problem is pretty easy to any calculator or any computing device. The point in here is that those two systems exist, and there are so many nuances. Like if you read this book, it talks about all of the different cognitive biases and all the different interaction between the two systems, which is a fascinating area of study. But the main point in making this argument for information visualization is that we can rely on both systems. If you take a look at the summary statistics, you're invoking your cognition. You're trying to think, well, the mean of the X, what does it mean? The mean of the Y, what does it mean? What does it mean for each one to have a variance? Let's think about it. If you're seeking the visualization, you don't invoke cognition, you invoke perception. So think about perception is a bonus, something added, everybody has it, and it's a very effective and a very high bandwidth way to communicate information to people. Indeed, the visual, the vision sense is a very high bandwidth. The highest bandwidth perception in a human being, it's estimated that the retina convey 1 gigabit of information per second to the brain. Of course, this is a crude estimate and there are so many assumptions made, but you get the point. Versus if you're trying to read, the bandwidth is so slow. It's probably on the level of maybe 5 bytes per second. Think about reading a phone number, right? How long does that take? So much, right? So the science and art of using visualization is to substitute cognition with perception. Something that we can communicate to other people and ask them to cognize about it, we can substitute it and communicate it in a visual chart so that they can perceive it immediately rather than think about it. Now, there have been many great books and papers. I mean, indeed, information visualization, it's now a standalone discipline, and there's many great scholars working in this area. It happens to be at the intersection of human-computer interaction, cognition, psychology, even biology. And there are so many experiments that these guidelines kind of build upon. What's the best way to create a chart, to create a figure? So what we're doing in this course, we're relying on what we call the grammar of graphics. The basic idea that any chart can be expressed by specifying some basic ways of creating the chart, basic constructs. And these constructs are called the encoding channels, the graphical marks, the data types. The main idea here is that, well, it's good, it's great that our perception system is very well developed and high bandwidth, but it also has limitations, right? I mean, an obvious limitation is probably that we only can perceive 3 dimensions. And realistically, when it comes to figure and charts, we can be only accurate about 2 dimensions. That's very straightforward limitation. We have limitations about color. We can only perceive a certain spectrum of color to a certain accuracy. We have also some biases when it comes to perceive things. You've probably looked at some of those eye twister, like you draw 2 lines that are exactly the same and tweak one, versus the other, and you get completely different perception of the length, right? So we have the human perception system is very developed, very high bandwidth compared to cognition, but it has its own limitation. And scholars in data visualization spend their careers trying to elicit best practices and guidelines to do visualizations. One of the key concepts is that we only have what we call channels, so many channels that we can use to create a visualization. Let's say I want to express two quantities. I can express them as positions on a common scale or a position on an aligned scale, and we can perceive that. I can express them as length, I can express them as tilt, as different areas, different depth, different shades of color, saturation of color, different curvature, volume, spatial region, color, hue, motion, and shape, right? And in each one of these channels comes with its own nuances. So it's very well known, for instance, that our perception system's accuracy to area is not very accurate compared to its accuracies to length. And this is very kind of well-known fact that pie charts are very they're not the best way to create charts, because people cannot perceive differences in areas, the proportions of areas, very accurately. Same thing happens when we do color, right? So there are many different, we can detect the difference in color, but we can't say a color is larger or smaller. What's the differences in shades are on the same scale, or perception's accuracies to length is much greater. So there are so many experiments on which the guidelines used in the grammar of graphics have been based. And this is just a rating of the different accuracies of these different channels. There are, I'm linking to these experiments. You can take a look at the other video. There are many of these experiments. So this concludes this presentation. We're going to revisit some of these concepts when we talk about the alter package in Python. I really invite you to take a look at the video I linked to, How to Think About Data Visualization in PyCon 2019 by Jake Vanderplas. This is the same person who is behind the alter package, which is a great presentation and also a good introduction to the package.